the July Next Energy webinar, which is sponsored by Royal Academy of Engineering. Today we have a really exciting topic on life cycle assessment um, for the passenger vehicle in South Korea. And without further ado, please welcome Professor Han Ho Song, who will talk about the LCA of greenhouse gas emission regarding the passenger vehicle in South Korea. I believe this is a really important topic, and we all very excited to hear uh, whether really using the electric vehicle is saving the world or not, and the holistic view of the carbon footprint of the electric vehicle. I think it's really important topic, and so without further ado, please go ahead with your presentation.
Okay, thank you very much for the kind introduction. And I'm Han Ho Song from Seoul National University. And then thank you very much for the invitation to this kind of great seminar and event. So today I'm going to talk about the kind of LCA on the kind of passenger vehicles in South Korean, the context, but it will give you also the sense how you can approach in your own research or study, and when you just perform the LCA on this kind of similar kind of topics in your in your study or in your in your kind of group. So the contents in today's presentation, and having kind of these four kind of the major kind of topics here. So firstly, because some audience might not be kind of familiar with this LCA in general, so I'm trying to introduce it and just using a simple word, and then also some kind of with some motivation why we need, or why people nowadays just are very much interested in this LCA in general. So, and that's the first one. And the second one, now we are moving on to the the more automotive and the oriented LCA. So focusing on that, the introduction to the automotive LCA, and then finally kind of getting into the automotive LCA result in Korea. And our group has been kind of researched on this topic since 2011. So it's more than 10 years we've done it. And so we're going to share the result out of it. And then finally, just based on this finding, and then we will just discuss. It's not really the complete, because this is only the future direction, we can just think about it and then we can discuss about it. So in the end, I'm going to just suggest some kind of future direction from the perspective of we want to reduce the GHG emissions, but from LCA perspective. So that will be the kind of last topic I'm going to cover in this kind of presentation. So let's start with this kind of first one, the LCA in general. And so to start with, and always showing you this kind of slide, and this is a kind of big picture of it. So, and then what this shows you, this is the emissions from the transport sector, and then the cyan color, and then this one is corresponding to the road transport. So this is the emissions, CO2 emission in gigaton worldwide, and then that's from this the passenger vehicles, trucks, and buses, and then those road transport basically. And then you can see that it's kept increased, and then until 2018, and then there's a COVID-19. So 2020 there's a significant drop, but after that we have some recover or increase it. And then but the thing is, this is actually based on this IEA's the net zero emissions by 2050. So if you want to achieve that net zero emissions by 2050, and the IEA suggests that in 2030 we need to have this the emissions level. We need to achieve it from the road transport, which is actually per year we should decrease the emissions by 2 gigatons CO2. So, and then that will be what should be needed to achieve that net zero emission by 2050. That's in IEA's report. And then to give you some sense how big the number is, so to decrease the 1 gigaton CO2 per year, and then how big that is, and you need to build the 130 of 1 gigawatt nuclear power plant instead of coal-fired power plant. You need to replace the 100 coal-fired power plant by nuclear power plant. Only in that you can decrease the 1 gigaton of CO2 emissions. So that's twice of it. That's a huge number. So we are not talking about the small number, and then that's actually a very challenging target, I can say. So in transport sector, in road transport sector, I should say, and then people are trying to developing the new technology and interested in the new technologies to reduce the GHG emissions. So these are the types of powertrain and fuels and powertrains available nowadays. And then firstly, this is the very first one is the conventional vehicle. So using the gasoline, diesel as a fuel, using the internal combustion engine as a power conversion device. And then that's the conventional vehicle, or ICEV, internal combustion engine vehicle. And you also know there is a hybrid electric vehicle. And then hybrid electric vehicle is still using gasoline and diesel as a fuel, but it's using engine yet. But still, there is some part of it is actually driven by kind of battery and motor system, and that's why it's called hybrid electric vehicle. But it's still depending on the gasoline and diesel as a fuel. And then next, and this is actually kind of big topic nowadays, which is the battery electric vehicle using the electricity as a fuel, and then the powertrain is only battery and motor. And then lastly is a fuel cell electric vehicle where the hydrogen is used as a fuel, and then using the fuel cell as a energy conversion device, that converting the hydrogen into the electricity, and then that electricity will drive motor to drive the car. So this is also the kind of new technology people are using to reduce the GHG emissions. So people are devising many different kind of the ways of reducing the GHG emissions. Then let me ask this question. So because by introducing the electric vehicle or hydrogen electric vehicle, people just people's intention is to reduce the carbon emissions out of the vehicles. Okay, so the first question might be very easy to answer. So between the gasoline-fueled internal combustion engine vehicle versus battery electric vehicle, which is more cleaner in carbon emission sense? So, well, there's no CO2 or carbon emissions out of the tailpipe of the electric vehicle, so it's cleaner, you may say. And then if you're comparing now, the second question is, so if you're comparing battery electric vehicle versus hydrogen fuel cell vehicle, and then in the hydrogen fuel cell vehicle, and then once the hydrogen coming into the fuel cell and then reacted with the oxygen from the air, then it will just only produce the water out of it. So meaning that there is no carbon emissions in the tailpipe. So then, comparing the battery electric vehicle and hydrogen fuel cell electric vehicle, which is better? Or they're the same? So these are the questions can be answered from somewhat different perspective, or just kind of having the wider scope of we can consider. So that's happening in this slide. So firstly, so what we've focused on is this tailpipe emissions. So again, internal combustion engine vehicle, there's a kind of carbon emission from tailpipe. And then the battery electric vehicle, there's no carbon emissions. Okay, that's fine. So we just compare it here. But the thing is, the gasoline is not really just, it's not from the air, right? We need to make it. So it's made from the crude oil and gotten into the gasoline. The same thing true for the electricity used in the electric vehicle. So electricity, again, should be made. And there's a power generation associated. And also the power generator or the power plant needs the fuel associated. So meaning that the electricity is not from nowhere, it should be made. So meaning that now we can think about, okay, so now which one is better if we also include in our study scope, including all these fuel production processes. So, and then emissions, greenhouse gas emissions associated with these processes, which is better? Now we can ask. Okay, so this is not actually the end of the story. So we can actually, just increase the scope further. So because the internal combustion engine vehicle versus battery electric vehicle, we know that in the battery electric vehicle, there's a big battery pack there on top of the just frame, right? Frame of the car. So meaning that that's different car. Having the different powertrain, it might cause difference in vehicle production. So thinking about the vehicle production, and then also that needs some raw materials and the parts production, vehicle productions, and then different vehicles can have different different things happening in their life cycle processes, and then that might change the emissions associated with that. So this is in this kind of the scope and then larger scope, wider scope, or life cycle thinking, that's actually what based the LCA study. So LCA, and then to answer for such holistic effects out of those larger scope of thinking, and then LCA is nowadays adopted very much widely, and then actually is increasingly adopted in many of the government regulation and rules nowadays. So it's getting important more and more, and it's steeply being important, I should say, in last couple of years. And then LCA, and from that, the holistic perspective is assessment of the environmental impacts. So LCA is about the environmental impact. It's not about the economical, it's about the environmental impacts. And then sometimes we call that is cradle to grave scope. It's having the cradle to grave scope or cradle to grave study, we call that. And then the cradle is like where we just put the baby and then baby just lying on it, and then that's the cradle. It's associated with the birth of something, right? And the grave, just that makes sense. This is the end of something. So it's cradle to grave, basically from the birth or from the start to the end. So that's what the life cycle is. So, and then to be more technical terms, so cradle to grave, associating these main the categories in it. So firstly, the raw material extraction is started with. So you need to just get some materials out of the ground, for example, and then out of the raw material, you're gonna make the more the useful material out of raw material, and then also you need to manufacture the parts and also manufacture the vehicles. And in the middle, you need to transport the raw materials and also the better material, and also you need to move around the parts, also the vehicle. And then once you make the vehicle, and then you need to transport that into the customer, or the dealer shop, for example. And then there will be some other transportation, and then all the distributions associated, and also uses phase. So because the product will be used, and then during the uses, there's also some consumable things during the use phase, and then all those things are also included in the life cycle phase. And then finally, at the end of the material of the product, and then there will be the disposal of it, and also some part of it could be recycled. So these will be the cradle to grave processes we typically say. And then to be more the exemplary, I'm just showing you this slide, and then this is the wind turbine. Let's see the wind turbine here. And then so from the raw material acquisition, so you're getting, for example, iron, carbon, sand, aluminum, copper, and zinc. And then out of that, you're gonna make more useful material to make the part or a part out of it. And then so out of the material manufacturing, you're gonna get the steel, concrete, fiberglass, silica, which are directly used in parts manufacturing. And then the parts manufacturing, out of the parts manufacturing, you're making all those components and making this wind turbine. And then once you make that, and then also construction can be included, and then the wind turbine will be used during the useful lifetime. And then at the end of its lifetime, it'll be disposed, or some part of it will be recycled. And then this recycling can provide material to this material manufacturing, replacing the raw material acquisition, so on and so forth. So this is a more concrete example, or as you can have, this shows you the examples how these are and then what's been included in it. So to give you some sense. Okay, so then once you have that life cycles ready, and then associating the parts and materials, and then associating processes and services already, then what you do is you are calculating the environmental impacts during those life cycle processes we just described. So throughout all these life cycle processes, you're coming up with the environmental impacts out of that. So those environmental impacts coming out of for example, the greenhouse gases, or particulates emissions, or during these processes, water can be used. So there is a water uses, And also, if there are some the toxic chemicals out of any of these processes, there could be the kind of toxic materials. And also, if there is any land use change during this processes, so you need to just cut all the trees out and then to make the plants there, and then that'll make the land use change, so forth and so forth. So these are just kind of small example, and then to give you some more, the bigger picture, and then this is actually what that is. So meaning that from those life cycle processes, you can just talk about all these different materials and emissions and then pollutants and or the small elementary flows there, and all these things are coming out of your the processes, and we call that as an inventory. And then those flows, now out of those individual elementary flows, you're gonna combine those together to come up with the impact category. For example, because currently just people are considering the climate change or greenhouse gas effect mostly. So out of these many different elementary flows, you're just getting the greenhouse gas species only, and then using the global warming potential value and making the CO2 equivalent mass in the end, and then that'll give us the overall climate change effect. And then the climate change, I know nowadays that's the main focus of this LCA study, but that's not actually the end of study, because the LCA is actually considering all these different impact categories we can think of. So ozone depletion, human toxicity, and even noise, and then acidification. So many different impact categories out of different elementary flows. But nowadays people are mostly interested in this climate change impact category. So that's actually just general introduction to the LCA, and then what it is, and then what it covers, and then how it's done. And then let's just move on to the second topic, which is the more specific about an LCA on the automobile. So we just call that automotive LCA. So then you can now at this point, so you might think that, okay, so we are talking about the life cycle, right? And that's too much of a scope. So because what is the life cycle, and then what's associated? So where is the boundary? And do we really consider everything around it? So that's the thing. So in ISO standard of the LCA, actually the first thing users should do, they should setting the objective of their LCA study, and then they also setting the system boundary or scope of your LCA study, and to achieve that objective you just mentioned, you just set. So meaning that when you perform the LCA, we need to set certain scope or system boundary to start with. So this is what it is. And then nowadays, typically when they talk about the automotive LCA, and then this is a typical scope. I'm saying typical because depending on the researchers, they might have somewhat different scope. And then different scope in a large sense, and also different scope, even they have look similar scope, but they can have, some details can be missing or added. So, you should be careful when you compare the result from this researcher and then that researcher, because they might have different scope, even they are talking about we've done the automotive LCA. So in general, when we talk about automotive LCA, they just consider two big life cycle. So one is the fuel cycle, and which is associated with the vehicle's fuel itself, like the gasoline, diesel, or electricity, or the hydrogen, for example. And then this one actually more called well-to-wheel analysis. We're going to come back to that well-to-wheel part in the following slide. So fuel cycle, basically. And then the next one is a vehicle cycle. And then this is associated with the vehicle product itself. So to make the vehicle, you need to just get the raw material extraction, material production, parts and vehicle production I mentioned earlier. So that's the vehicle cycle. It's about the product making. So that's a vehicle cycle. And then as a whole, just adding fuel cycle and then vehicle cycle together. And then that's what people typically say automotive LCA, or that scope of it. So this, I'm going to just give you some more details in the following slides. So, okay, what we have done so far in our research group. Okay, so we adopted kind of Greek program, and then this Greek program is the kind of this Excel-based program, and then this just being the framework of our LCA calculation. And then the originally Greek program is from the US Argonne National Laboratory, and then we are using that framework, and then but we need to change all the major data inside it, because the Korean situation is different than US situation. So meaning that into that framework, and then we just kind of put Korean specific data. And then that was actually taking time. And then even we are taking time now also. And then since, again, 2011, we started this work, and then we are just referencing the domestic data and foreign data, and also we are partnering with all these associations and then the vehicle OEMs to get the better data. So as a joke, we just typically as a joke when we talk about the LCA, we just call it this way: the garbage in, garbage out. So meaning that if you just kind of put the bad data into it, the result out of it is not any good. It's not doing any good. So the data is actually the key to this LCA analysis, and then there are lots of data needed, as you can imagine, because we are talking about the life cycle. Okay, so let's be more specific about the fuel cycle. Okay, so fuel cycle, and then let's just see this diagram below here, and this is the typical gasoline-fueled internal combustion engine vehicle. So to use that fuel in the vehicle operation in the end here, and then the gasoline is actually, the gasoline's life cycle starts with this crude oil recovery or extraction. And then this crude oil will be imported into Korea. So there is a crude oil import process. And then there is refinery there. So the crude oil coming in and then the gasoline out of it. And then gasoline will be distributed to the the local gas stations. There's a fuel distribution nationwide. And finally will be charged into the fuel tank of the vehicle. So up to this point, we call that as well-to-tank processes. So this is basically upstreams of this kind of fuel being used in the car. So this is the upstream processes, or well-to-tank. Well is this crude oil well, and a tank is the fuel tank of the vehicle. And then this vehicle operation, which we typically look at so far, and then so from the tank, the fuel in the tank, and then it should be used in the internal combustion engine, and then to drive the car or drive the fuel of the car. So that's the tank to wheel processes. And then so this is the vehicle operation in the end. And as a whole, this is a well to wheel processes. So and then this is a fuel cycle, typical fuel cycle. And then in this study, I'm showing you this the result today. And it's including the only three greenhouse gas species, the CO2, CH4, and N2O. You know that there are many other greenhouse gas species out there. And then these are three major greenhouse gas species. And then we are using the global warming potential, and so to convert that methane and N2O into the equivalent CO2 value. And then finally, we're going to just express the result as a CO2 equivalent mass in the end. So this is about the fuel cycle. And then talking about the vehicle cycle, and then again, now you got the sense what the vehicle cycle is. It's about the kind of vehicle production. And also we are kind of talking about, but the one thing I need to point out, this is not just making of the vehicle, it's also uses of the vehicle. So meaning that during the use of the vehicle, there is a certain maintenance material is used for your vehicle operation. For example, you need to change the tires during the lifetime. You need to change the engine oil during the lifetime. So meaning that those tires should be made from some air. So there's a life cycle associated with your tire. Also, there's a life cycle associated with your engine oils. And so meaning those also be included. And then again, this was a recycle once the car is just at the end of the useful life. And also the same greenhouse gas species we've considered. And then to give you some sense, okay, so we're going to see the quantitative number later on, but to give you some sense, because our original motivation of this vehicle cycle is, okay, so we are talking about the battery electric vehicle and then fuel cell electric vehicle. How different as compared to the internal combustion engine vehicle in this kind of vehicle cycles emissions? And then let me tell you, as a rule of thumb, the battery electric vehicle and fuel cell electric vehicle in the same class of vehicle that emits 1 times or 2 times of the greenhouse gas emissions during the vehicle cycle only. Okay, so but we're going to see the quantitative number kind of in the following slide. Okay, so this is about the vehicle cycle analysis, and then the scope of fuels and powertrain we've covered in this study. And then from the fuels perspective, and we will consider gasoline, diesel, LPG, and also the natural gas. And then, but in today's presentation, we're going to only focus on gasoline and diesel. And then also for the electric vehicle, we have the electricity as a fuel, and then also the hydrogen as a fuel for the fuel cell electric vehicle. So from powertrain's perspective, we consider the internal combustion engine vehicle, ICEV, and also the hybrid electric vehicle, HEV, and also EV and FCV. So those will be covered in the results section, but basically kind of what you've seen here, and then we actually kind of done the kind of whole things in our study, but we will focus on some part of it. Okay, so finally, let me move on to the kind of results section. So in this results section, and it actually consists of these three kind of subsections. And firstly, we're going to start with the fuel cycle results. So meaning that we're going to focus on the fuel cycle or well-to-wheel processes only. So that's the first part. And then now we're going to switch gear into the vehicle cycle result. So we're going to talk about only the vehicle production, the result. And then finally, we're going to combine these two results together to come up with the combined result or the holistic kind of result or the whole scope result in the end. So we're going to just kind of go one by one. So let's start with the well-to-wheel or fuel cycle result. And then this slide, I'm just preparing to introduce you to how to see the result. So this is just example, and then the real result following. So, and then the well-to-wheel GHG emissions will be shown in gram CO2 equivalent per kilometer basis. So what that unit means, so if you're driving the car in 1 kilometer, and then this gram CO2 equivalent emissions happening during this whole fuel cycle processes or well-to-wheel processes, that's what it is. So if you see the left figure, which is about or example about the internal combustion engine vehicle, gasoline fueled, and then see this the plot over here, and then this shows you about 210 or 20 grams CO2 equivalent per kilometer. So again, if you drive a kilometer, 1 kilometer, and then that's how much of life cycle emissions or fuel cycle emissions, that's what it is. And then if you see this plot, there is a gray section, which is the vehicle operation. That's the big chunk of it, right, from the fuel cycle. And then that's the vehicle operation, meaning that's the tank-to-wheel emissions. So that's the tailpipe emissions. So meaning that, okay, so we've done this much of the job to come up with this fuel cycle emissions for this internal combustion engine vehicle, crude oil extraction, refining, and all those things. But in the end, this fuel cycle emissions is dominated by tank-to-wheel process or tailpipe emissions. That's the typical characteristic of internal combustion engine vehicle. So even though you're considering well-to-wheel emissions, the emissions is dominated by the tailpipe emissions. And then we still have the emissions emissions from the well-to-tank processes or making the fuel, right? And then these include that, the crude oil extraction, refining, and everything. So this is what it is. And if you go to the right side, which is the pure EV or battery electric vehicle, and I see left figure first. And then we have some lower well-to-wheel emissions, fuel cycle emissions, like 110 or so. And then you see that there's no gray expected, right? There's no tank-to-wheel emissions because this is an electric vehicle. There's no tailpipe emissions. But this orange color, this is the power generation. So meaning that this is from this is the GHG emissions associated with the electricity generation. And here we are just showing you the case, natural gas-fired power plant in this case. And then so you see that there is a much of greenhouse gas emissions from the power plant stack to produce the electricity to drive the car. So for the electric vehicle, it's still not zero emissions, as you can see. And also there is a kind of this blue, and this blue is associated with the power plant fuel. In this case, natural gas, because this is a natural gas kind of fueled power plant. So this kind of blue associated with this preparing the natural gas and then getting into the power plant gate to be used to do the power generation. So, EV case, and then definitely there's no tank to well emissions. This is just well to tank emission dominant or just well to tank emissions only. Okay, this is how you see the result, and then let's see the real result. And then this well-to-wheel GHG results is it's from the all passenger vehicle sales in 2019 in Korea. So we just have this, the passenger vehicle sales data, and then we do the weight average by sales volume of all those models considered. And then we categorize it into the internal combustion engine vehicle fueled by gasoline, diesel, and also the hybrid electric vehicle and fueled by gasoline. There's no diesel hybrid electric vehicle in Korea. And then the battery electric vehicle and fuel cell electric vehicle. Why there are three of them, I'm going to just come back to that later. So let's just compare the average value. So you see that the gasoline internal combustion engine, diesel internal combustion engine, hybrid, actually it can decrease the fuel cycle emissions hugely. And then it still have higher emissions than battery electric vehicle. So you should see this kind of plot down here. And then this kind of yellow dot is actually the compact vehicle, and it's saying best. What that means is we are talking about the fuel cycle emissions associated with the compact size vehicle with the best fuel economy. So best efficient compact size vehicle. So if you just gonna pick that out, and then this yellow gonna tells you that. So meaning that this yellow tells you what you can do best, having the fuel and powertrain combination in that analysis. That's what it is. So you just see that, if you just see that in that way, and then now the best hybrid electric vehicle is still higher than best electric vehicle, but it's not that far anymore from the fuel cycle's perspective. Then, so let me just be more specific about how we come up with this battery electric vehicle, this one guy over here. So we're going to come back to this slide. So let me just gonna go this next slide here. And then this is how we come up with this first figure. This is the average Korea mainland average, the result. What it is we are considering the power generation mix to come up with the number. So, in some statistics and in Korea, and we know every power plant in Korea, and we know every power generation amount throughout the year, certain year, and also every fuel uses in that specific power plant throughout the year. So we can come up with the efficiency out of that plant and also emissions out of the plant. And then so that's how we come up with this generation mix. And which mainly consists of coal-fired power plant, natural gas-fired power plant, and a nuclear power plant. So, and then we just use that mix of that power generation to come up with that mixed number for the electric vehicle. And also we consider that electricity transmission loss, because from the power plant and then to deliver it into the charging station, there will be the transmission loss, and they should be considered in the life cycle of that electric vehicle. And then, so that's what that number. And then the other two guys on the right side, this is still the battery electric vehicle, but we are just showing you some number. And then this is the coal. It's saying coal. What that means is, so if you are using the electricity from only the coal-fired power plant, and what will be the fuel cycle emissions? That's huge, as you can see. And if you see the best compact number, that's just compatible to diesel or gasoline, right? So this, that means coal-fired power plant having a larger emission, and it doesn't help in the battery electric vehicle. And if you're talking about the natural gas-fired power plant, and actually that's very compatible to the mix of it, and then also very good numbers there. So, and the natural gas-fired power plant, it has higher efficiency, and also natural gas itself has lower carbon content in it. Okay, so that's just more than enough about the battery electric vehicle. Let me move on to the fuel cell electric vehicle. So if you see the first one, this again is some kind of Korea average there. And then that's that was done similar way. I'm gonna show that in the next slide. So anyway, this is a very small number as compared to the others, right? And let's see how we come up with the number first. And then we're gonna come back to this slide to talk about the other twos. Okay, so you know that the hydrogen is not really from just digging the ground, right? And hydrogen is actually a secondary fuel, so meaning that you need to make one from other fuel, right? Primary fuels. And it should be produced. And then there are many different ways to produce hydrogen. And then, so what we've done in our study, we know the hydrogen gas stations throughout the nations, throughout the country, and then we know how much of the daily the filling capacity they are running on per day per stations, and then we also know where they're getting the hydrogen from. So meaning that certain gas station, hydrogen gas station, using the hydrogen from the naphtha cracking or petrochemical industry, byproduct hydrogen we typically call, and then some using the SMR-based the hydrogen, and then some using the electrolytic hydrogen. So we have these the different stations using different hydrogen sources and a different amount, so we can finally come up with some kind of share. And then it comes out that, and then 95% of that the hydrogen used as a hydrogen fuel cell vehicle, and then out of this petrochemical industry or from the naphtha cracking as a kind of hydrogen being as a kind of byproduct, and then some part of it being SMR, electrolytic hydrogen. So using that and then doing the life cycle analysis of that hydrogen production process, and then that will be the part of the calculation. And then the other important thing about the hydrogen is about distribution and storage in their life cycle. And as you all know, the hydrogen is one of the lightest kind of molecule. And then in the ambient state, the volumetric energy density is very, very low, right? So what that means is to move that around, to distribute it. So you make the hydrogen in a certain plant and then move it to the charging station. You need to distribute it, right? And then to do that, they typically do the compressing on the hydrogen. And then they're using the 200 bar compressed hydrogen in the tube trailer. And a tube trailer is like the tanker of the hydrogen. So tube trailer is the hydrogen tanker, basically. And then so in that pressure, it's really high pressure. But even with that, in Korea, there's a huge hydrogen tube trailer, but that only carries per truckload, there only carries about 300 kilograms. So to compare the number with the gasoline, the biggest gasoline tanker per truckload, it can deliver 25 tons per truck. So you see difference in other magnitudes per truckload. And even when you consider the heating value difference, the hydrogen has higher heating value. Even with that, to deliver the same amount of energy, you need to do 30 times of trucking to deliver the hydrogen because of that, because of the lower energy density. And also, the typical hydrogen plant produces the hydrogen in 10 bar-ish pressure. And then, the fuel cell tank in the fuel cell electric vehicle is 700 bar. So meaning that from 10 bar hydrogen produced, and then you need to store it in the car at 700 bar, meaning there is compression processes during this life cycle of the hydrogen finally getting into the fuel cell vehicle. And then that is actually done by the electric compressor in Korea, meaning that consumes electricity only to compress the hydrogen to store in the car. And then there is life cycle emissions associated with that electricity use for the hydrogens, the hydrogen's life cycle. That takes the energy, and then that takes the emissions associated with that. Okay, so that's what that is. So this Korea average, the fuel cell electric vehicle, hydrogen produced mostly from the petrochemical industry. And then the other two is, again, this NCC is the naphtha cracking center, or that's what I just mentioned, is the petrochemical industry and the byproduct hydrogen. So a very small number, because this is 95% of this guy. And then finally, on the rightmost, and this is the SMR, or steam methane reforming process. And then so from natural gas to hydrogen, and then or we call that gray hydrogen nowadays. And then if you're using a gray hydrogen, okay, see the number, that's not at all make sense. Even if that's fuel cell hydrogen electric vehicle, if you're using gray hydrogen as a fuel, there's no way to make sense using the fuel cell electric vehicle to reduce the GHG emissions. So this is actually enough about the fuel cycle, and let me move on to vehicle cycle. Actually, vehicle cycle is much more complicated than fuel cycle, but I'll be very brief because there are too much of things going around. And then, so when we talk about the vehicle cycle emissions, as a rule of thumb, the amount of materials used will be the key factor in vehicle cycle emissions. So meaning that if you have larger vehicle using more materials, will have more vehicle cycle emissions. Clear, right? I mean, that makes sense. So no doubt. So that's one big key things, easy thing to understand. Now, let's focus on the difference here. Difference between internal combustion engine vehicle and battery electric vehicle, and internal engine vehicle and fuel cell electric vehicle. So what's different with this different powertrain? What will be the kind of key difference from these new vehicles? So let's talk about the battery electric vehicle first. And then you can imagine that, right? So battery electric vehicle, the key difference is battery. That's the big thing as compared to the internal combustion vehicle. So firstly, in contemporary battery electric vehicles, the vehicle weight, the 20 to 30% of the whole vehicle's weight is actually battery pack. That's huge number. So meaning that internal combustion engine vehicle has 1.5 ton for compact class, and then you are adding 20% of the whole mass on top of that. That's what it is. So again, I mentioned that if you increase the amount of mass, you will increase the vehicle cycle emissions. But there's also the bad things about the battery production, and not about the bad thing, or the energy intensiveness about the battery production there is. So we just kind of go through many different literatures with the many different manufacturing capacity, and then finally we come up with this number. So if you increase the factory size, and then to produce the per kilowatt of our battery, and then there is so much of energy will be needed, and then it'll be decreased with the larger battery factory capacity, but it's gotten saturated. If you just have big enough factory, it's gotten saturated. There's no more decrease. So we are using this number, but that number is still energy intensive. So that makes the huge vehicle, the life cycle emissions associated with the battery electric vehicle. That's one big thing about this battery electric vehicle. And then for the fuel cell electric vehicle, so you may think, okay, that's the fuel cell, right? No, actually fuel cell, that contribute the additional emissions, but it's more from the the hydrogen fuel tank, the high pressure hydrogen fuel tank. And typically the mainstream is a Type 4 tank nowadays using, and a Type 4 tank, this is the composition of it, and it's using much of CFRP there. And a CFRP, you know that it just consists of carbon fiber and epoxy mostly. And then this carbon fiber is made out of very high temperature processes. And then that takes the energy, huge amount of energy. So meaning that to produce the hydrogen fuel tank, that takes the energy. That makes a huge difference. Okay, so about just kind of being simple here, but there are too many things around the vehicle cycle, but to give you some kind of big intuitive kind of way of understanding it, that's how I'm kind of focusing on. And then let's see the result. So this is the vehicle cycle GHG results only. Okay, it's about the vehicle cycle. And then again, same kind of group of vehicle sales in 2019. And then I have the 4 different groups. Here is a small sedan and a large sedan, small SUV and a large SUV, because different class of vehicle will use a different amount of materials. And then I just mentioned that different amount of material, different emissions in vehicle life cycle. So, and then there are all similar studies. So let's focus on the small sedan group only, and then you can see others in your own time. And then for the small sedan, and then let's see, and this is the internal combustion engine, gasoline vehicle, and then diesel vehicle, hybrid electric vehicle, battery electric vehicle. And then this is the 200 kilometer it can cover, and this is the 400 kilometer it can cover. And then finally, fuel cell electric vehicle. And then firstly, let's see the kind of blue here. And then blue is components. And then you see that because they are all small sedan, so using the similar amount of components there. So there is slight change up and down, but they are more or less the same. And then, but the fuel cell electric vehicle, it has a large amount of components emissions. And then that's from mostly, that difference is coming from mostly hydrogen tank I just mentioned. So that's big additional emissions associated with it. Okay, then fluids, and this is the engine oil and then all kinds of fluids you can imagine, and they're a small portion of it, so it's not really huge effect there. And then the green is ADR, which is the assembly, disposal, and recycle. So you're making up the parts, you're making up the vehicle, and then disposal and recycling, and then that's what that green is there. It's all throughout the same, basically. So, and then finally, if you see this kind of magenta, this is the batteries, and then you see is everything, every other thing the same between internal combustion engine vehicle and a battery electric vehicle, more or less. But on top of that, you're adding battery pack on top of it. So that's actually a huge increase in the vehicle cycle emissions as expected. So this is actually how you understand this kind of overall result. And then finally, let's combine this fuel cycle and a vehicle cycle result together. And then left, we have a specific vehicle here. Now, it's not about the average. This is a specific vehicle most sold in Korea at the time of the study. And then the left 5 is about the compact size vehicle. So gasoline, diesel, hybrid electric vehicle, battery electric vehicle, and then shorter range, 240 kilometer, and a longer range, 360 kilometer it can cover. And then you see that. So, overall trend remains same. So gasoline, diesel better, hybrid much better. And now battery electric vehicle comparing with the hybrid electric vehicle, you see that by adding this yellow, which is the vehicle cycle emissions, on top of the well-to-wheel emission, fuel cycle emissions, they are more or less the same. Or if for this larger distance, and then that one is actually slightly higher emissions in the end. So at this moment, hybrid electric vehicle is very compatible with the battery electric vehicle from life cycles emissions perspective. If you go to the right, which is about the SUV class, and then again, gasoline, diesel, hybrid, okay, we have same trend, but now see the battery electric vehicle here. This is a Tesla Model X, and then that one has actually very large emissions. And then most of the emissions coming out of this orange, again, orange is the power generation, meaning this is a big vehicle. SUV is already heavy. And then you just put the big battery pack on top of it, much heavier. So meaning that will have very bad fuel economy out of it. So meaning to run kilometer of the vehicle, you're gonna need huge amount of electricity. And then so power generation in a power plant, there is a huge amount of emissions. That's what it is. And also, this yellow is huge, it's very big because it uses large battery pack because this is the SUV, you want to cover the large distance. So you have large battery with this lower efficiency, that's even larger amount of battery you're gonna need. So that's what causes this big emissions. And then finally, rightmost is the fuel cell electric vehicle. And then if you're using byproduct hydrogen, it still looks okay. It looks good, actually, I should say. But if you're using the gray hydrogen, that's not good anymore. So the same story, but just more specific about the specific vehicle we're talking about. Okay, so finally, the last kind of chapter of my kind of presentation, and then this is the future direction. So now we've seen that LCA-based GHG emissions, and then what is the characteristic of them. So I think you already know the answer. So what we should do, but let's be more specific and then be more quantitative here. So it will be kind of short kind of sections. So let's coming back again to IEA study, and then again saying net zero emission, the scenario by 2050. So what should happen in 2050? So this is the global energy flows in 2021 or current, and then this is what should be done in 2050 to achieve that net zero emission. That's what it is. So I know it looks complicated. So let me just point out several important things here. Firstly, in 2021, you have oil, coal, natural gas. These are three major fossil resources we are using to produce all the end use here. This is the end use. This is the resources. But in 2050, these are a very small portion of it should be. And mostly from carbon neutral resources you need to use. So wind, water, solar, nuclear, bioenergy, and other renewables, and then those things should be done. And these are the NDUs again, back again. And then the other thing is, the difference is hues yellow, right? Compare then yellow here, yellow there. That's the electricity. So meaning that to do the natural emissions, and then we need to use electricity in the end use. Most of the end use, you need to use yellow. And then that yellow coming out of these carbon neutral resources. That's the other thing. And then I need to point out, because we are talking about the automotive LCA, so you see the cars, trucks, and then these are using all yellows there. So meaning this, you need to use a renewable electricity in your car to reduce the emissions or achieve the natural emissions. And then the other important thing, because you are talking about the vehicle cycle emissions already, and then you need to make the steel, and currently steel here in 2021 is made from coal, right? It's coal-based steel we are using for the car, for example. But at that time, it should be based on renewables. So it's renewable, renewable electricity and used for the steel making. And then that should be done to reduce the vehicle cycle emissions in the vehicle industry. So that's what should be done. That's the first thing in this kind of the paragraph here. And the second thing is, so there's no big pink here, but now we see this big pink here, which is called hydrogen, right? There's a hydrogen there, but this hydrogen is big here. So here, this hydrogen made out of this yellow, and then this yellow is all green, right? Or carbon, the carbon-free sources from carbon. So that's the green hydrogen you're using. And then this will be also fed into these trucks and then ships. So in the transport sector, you're using hydrogen, clean hydrogen. And also some hydrogen coming out of this natural gas. So this is the SMR, but still it's talking about the CO2 capture with the SMR, meaning blue hydrogen, not gray hydrogen. So overall, this green blue hydrogen we call clean hydrogen nowadays, and then that also plays an important role in transport sector in the future. So then, how much of the effect will be done in quantitative sense? So let's talk about the battery electric vehicles future. So this leftmost is the current emissions, and then we have the vehicle cycles emissions, and then the well-to-wheel emissions. Everything's together. And then this is the specific model, BMW iX SUV model. And then, okay, so let's adopt the carbon neutral electricity in the grid. And then we are using the 2030 generation mix in Korea, moderate expected mix, and then aggressive mix. And the moderate mix include the 20% of renewable from 5% currently. And then the aggressive mix is 30% renewable, including the grid. So then you see that there's a huge decrease in overall life cycle emissions. And then once you have that, and then how about just increasing the fuel economy? So let's improve the vehicle itself, and by 5%. You may say 5% by 2030 should be more. No, actually, this is actually we consulted with the vehicle OEM, because the electric vehicle is already fuel efficient enough. And a 5% improvement in fuel economy is not that easy job. So anyway, let's do that. Assume that 5% increase can be possible. Even with that, you see that there's not much increase because it's already efficient. So there's not much gain. So the fuel economy gain will be minimal from the battery electric vehicle. And then finally, there is a kind of big chunk of vehicle cycle related emissions. And then to reduce that, you need to do the careful battery recycling. And also, I just mentioned that clean material production, like the not coal-based steel. You need to have the renewable steel or the aluminum made out of renewable electricity, so on and so forth. So to reduce this vehicle cycle associated emissions. And if you talk about the hybrid electric vehicle, so let's just apply that the grid electricity there. You see, I mean, even with the 30% renewable, there's not much decrease because in the end, hybrid electric vehicle is not depending much on the grid electricity. It's depending on its own. its own efficiency, meaning its own engine's efficiency and system's efficiency. So to confirm that, we increase the fuel economy of that vehicle by 15%. Again, this is the number achievable by vehicle OEM confirmation. So 15% improvement, then you see that there's a huge decrease in the greenhouse gas emissions, life cycle emissions there. And then finally, the last one is the e-fuels use. So what I mean by e-fuel, this is a synthetic fuel coming out of green hydrogen. You see that the hydrogen from renewable sources, the green hydrogen, and then the carbon from the air. So you're doing direct air capture, DAC. And then using the hydrogen and then CO2 out of air, and then you synthesize the hydrocarbon fuels, basically. You synthesize gasoline or a diesel. So that's why it's synthetic fuel or e-fuel. And if you're using the e-fuel, and then this e-fuel, because you're from the carbon, the neutral sources, and then it has zero life cycle emissions or small life cycle emissions. And then if you include that in the fossil gasoline, so here in this case, we are only mixing 10% of e-fuel into the 90% of fossil gasoline. And then even with that 10%, the mix of the fuel, that can significantly decrease the life cycle emissions. If you increase that number of the complete or the e-fuels used, then you see what will happen to that kind of decrease in the GHG emissions. Finally, fuel cell electric vehicle. So here trying to show you, okay, so we've already known that, the fuel cell electric vehicle is the life cycle emissions associated much dependent on how you make the hydrogen as a fuel, right? So we are showing you different hydrogen production pathways and then associated the fuel cell electric vehicle's life cycle emissions. So depending on how you make it, that's huge difference, right? And then to give you some kind of future of hydrogen, this kind of blue dotted line, it's based on use of clean hydrogen. Okay, so again, the clean hydrogen, and then depending on the kind of definition by researchers and also the kind of the countries, but that typically, and that's defined as the hydrogen produced with the 60 to 70% life cycle GHG emissions reduction as compared to the gray hydrogen. So what I mean by that is when you produce the gray hydrogen, there's so much GHG life cycle GHG emissions, right, to produce the gray hydrogen. So you need to reduce that by 6 to 7%. And then if you can produce the hydrogen in that way, that's called clean hydrogen. And then the blue dotted line is showing you the life cycle emissions associated with the fuel cell electric vehicle if you're using the clean hydrogen. So that is kind of threshold and below. If you make it green hydrogen, it will be zero, right? Well, associated with the hydrogen production itself. And then as you compare that with the future battery electric vehicle and a future hybrid electric vehicle, that's very competitive. If you're using the clean hydrogen for your fuel cell electric vehicle, that being very competitive in the automotive LCA perspective. So this is actually end of my presentation. And then again, to kind of emphasize and then to understand the holistic effect of a new technology, LCA is increasingly adopted nowadays. And then that's even adopted in government rules and regulation nowadays. So it's getting kind of more and more important. And then from the LCA point of view, it's not really, okay, so use the electric vehicle, use the fuel cell electric vehicle. That's not the end of it. You need to see the holistic effect of it. And then from the LCA point of view, even the hybrid electric vehicle with the internal combustion engine can have the possibility to reduce the GHG emissions. And also the battery electric vehicle, fuel cell electric vehicle, they have different perspective. They have different strategies to reduce the GHG emissions to achieve the carbon neutrality in the end. So, and then all the rest of them is actually repeating what I've just mentioned so far. So I think I need to stop here. And then thank you very much for listening. Thank you.
Thank you very much, Professor Song. It's really exciting to hear, and also very shocking to see that, what I believe so far, that I'm using electric car, And when I see the result of like the life cycle assessment, yeah, I start to doubt. Oh, okay, whether this is am I helping the world or not? Um,
Okay.
but yes, you mentioned. Let me start with some question about the holistic picture of this LCA
Okay.
movement. So you mentioned that LCA is about environmental, not about economic. But
Mhm.
I feel like many countries now they put economical incentive
Mhm, mhm,
for people to do LCA. And does that affect your work? For example, who sponsor you to do the LCA, and you have to adjust parameters. Like how do you keep your integrity when doing this LCA thing?
mhm, mhm, mhm.
When economics is involved.
Yeah. So typically, LCA study is always many of the good studies actually is alongside with the TEA we call is techno economic analysis, and then TEA is basically the life cycle cost analysis.
Mhm.
So they're actually going kind of together in many of the kind of study. And also, I mean, you as point out from the government point of view, kind of both aspects are really important. So they need to see the environmental impacts and also the this cost effect. And then environment impact is like, okay, so you need to reduce it, and then we know, this, we're gonna we're gonna give more incentive to the lower emissions technology overall from the life cycle perspective. But how much, right? How much I need to give you more incentive to certain technology to come up with that number? You definitely need to have, okay, so what would be the kind of how much more cost you need to invest in that lower emission technology, and then the gap should be made up by these incentives, ideally. So that's actually what government do. So you do both study at the same time, and with the same, all the parameters and then things together. And because if you're using certain efficiency in the life cycle emissions and then different efficiency in the economic analysis, that's all wrong because you're talking about different energy uses. So meaning they need to go, in parallel to come up with kind of better result in the end. That's for sure.
Yeah, and I'm not regarding the hydrogen part. You mentioned there's
Mhm.
the clean hydrogen from naphtha cracking, and then you have the steam reforming, methane reforming, and then you have
Mhm.
electrochemical hydrogen, green hydrogen. Um,
Mhm.
so I'm not sure why do you not consider the carbon emission from the naphtha cracking process and consider it as a clean hydrogen?
Okay, so actually you're kind of poking at a very sensitive issue nowadays. I'm also working on the clean hydrogen certification scheme system in Korea myself. So I mean, just there are many countries kind of working on this kind of the program, clean hydrogen program, and then do the incentive on it. And then Korea also doing it. Actually, we just started, and we just started the government program. So I think this is a world first. I mean, the U.S. working on it, UK working on it, Japan working on it. They're working on it, but they've not started yet. But Korean certificate, Korean higher certification system is already started. But okay, so that's a side story. But the thing is, green, blue, that's clear. That's clear. There are, if you do the much of capture from the SMR process and then being blue, and then that might be considered clean. But the byproduct hydrogen, that's actually in the middle, very sensitive, the part. So firstly, you see the kind of very small number, right? Very small number with the hydrogen process
Mhm.
here,
Yeah.
hydrogen production here. What's happening there? So from the naphtha cracking, that also including all the crude oil extraction, and then getting the crude oil into the refinery in Korea, and then make the naphtha out of it, and then it's coming into the naphtha cracking center, and then there's all other hydrocarbon products, and there's a small portion of the hydrogen there. That's that hydrogen. So meaning that life cycle, that small part, is actually considering all upstream processes. really. That's including that. But the thing is, what happens here? Because that hydrogen is produced with other hydrocarbons, and then what we do in life cycle assessment, we allocate the emissions, whole emissions, into these different products. So we allocate all these emissions into the hydrogen and also the ethylene, propylene, and other things. We just allocate them. And then the other important factor is that you put the carbon into it, right? Naphtha is a carbon, hydrocarbon, or it has a carbon in it. And then you can see that most of the carbon will become the product out of it, right? Propylene, ethylene. So meaning that there's no carbon emissions. Carbon is actually going as a product out of the system.
I see.
So hydrogen looks clean, but the thing is, that's not how it's considered in this clean hydrogen certification, not in that way. So that's why I'm saying it's kind of more complicated. It's kind of story, but okay, let me explain it, if I can explain it good. Okay, so what's happening is that byproduct hydrogen is already used in that petrochemical plant. You know that. That's not really being sold outside. If there's some leftover from time to time, it's not really always. It's all used in the petrochemical plant to produce the heat, mostly. So what that means is, okay, from clean hydrogen certification program, government perspective, because by introducing this clean hydrogen program, we want to reduce the greenhouse gas emissions from using it, right? By using it. But what happens here is this. So if the manufacturer, the petrochemical, the plant or the company, if, okay, they decided, okay, so is this clean hydrogen? Okay, let me sell that as a clean hydrogen, and now let me have some incentive from the government. Okay, so once you do that, what happens is, because you need to still run the same process, right, in the factory. What that means is, if you sell that hydrogen outside, then you need to compensate certain amount of energy. Typically, that's done by natural gas, meaning that that company will purchase natural gas to compensate for that hydrogen sold.
I see.
Meaning that from the government perspective, that increase of that GHG emission increase associated with that natural gas uses, life cycle emissions associated with that uses, that's the responsibility of that hydrogen you just sold. Then what we do is, from the LCA, we add that amount of emission to hydrogen. That's your responsibility. So then that will not be this amount of emission. On top of that, there is that additional value, and then that'll not going to be clean hydrogen anymore.
I see. Yeah, very clear. And I have another question regarding. It's quite shocking to me because when you said, oh, electric vehicle, the battery one, and then the fuel cells that produce 1.5 more, greenhouse gases per kilometers compared to the ICE one. My first thought would be, oh, but the hydrogen fuel cell use a lot less battery because it just needs small battery to run. But then you mentioned that most of the carbon emission from car manufacturing come from the tank, right? So why is the tank releasing so much carbon dioxide when making? And yeah, it's just quite surprising because I would imagine extracting all these elements to make battery would produce more carbon emission than making like a tank for hydrogen. Can you elaborate more?
Yeah, that's actually very kind of the important question and the very good question. So because I'm just gonna skim through it, so I didn't make myself clear here enough. So so this is the additional one, right? You still need to have the same frames and things and the seats and tires and the same thing. But the thing is, when you make the kind of this high pressure hydrogen tank, and because you need to, that's a small molecules, and then it just had to tend to, just solidify the materials easily. It's just gonna penetrate through the kind of materials and make it kind of brittle and then things. So, and then think about the high pressure, like the 700 bar, and then that'll even have more tendency on it. So that's why the hydrogen fuel tank is being special, not like the gasoline tank. And then so that's just being made out of this kind of CFRP, much of it. And then that means, in our vehicle kind of life cycle, and then there is a kind of CFRP made in some part of the kind of life cycle. And then that kind of making the CFRP, that takes a lot of energy because it's just made out of carbon fiber, much of the carbon fiber. And then carbon fiber is not really kind of easily made. And then that takes the energy. So that's what it is. That's actually exactly why we need to consider kind of these types of study, because we don't know. I mean, until we really kind of done the number, we don't know how big that number will be. Because before that, tank, hey, that's tank. Well, what's special about it, right? I mean, just the gasoline tank is there and the fuel cell tank is there. What's special about it? But it comes out as, and that's not the really study. I mean, but I'm not saying this is some kind of snapshot at the time of study. So we don't know in the future and how the process will be kind of better in the kind of the efficiency and also using less carbon intensive kind of fuels to do that, and then so forth and so forth. Then we can just clean up all those emissions in those life cycle perspective. Then we can reduce overall emissions in them. But that's again and the snapshot at the time of study.
Yeah, got it. Can you go to the energy flow slide, please? The global energy. Yeah.
Yep.
Yeah. So because my research is on hydrogen. So when I see this, seems like the prediction, the direction would be to electrify most of the sector. Is that the case? For example, I would think that maybe hydrogen could help with the iron and steel industry, can fit into chemical industry. It seems like here most of the thing hydrogen do is energy to heat, and then the transport, the big truck transport.
Yeah, I mean,
you agree with this, or do you have any opinions?
You know what? Actually, I can. It's not kind of easy to say, how it'll be done in the future, right? I mean, this is a kind of too much of a kind of big study I can just argue against. But the thing is, what you mentioned is you can use this hydrogen to do the kind of steel making instead of coal as a kind of reductant, right? I mean, that's one thing you just mentioned. And then, I think that Ocean is actually that guy over there, and then kind of going to the industry, and then it's hard to see, but we are talking about the global scale. So this, small, tiny line is not really small, we should say. That's actually a huge amount, we can say. And but mostly, this is what I'm thinking. I mean, because we are from transport sector. When you think about the transport sector, we are typically just focusing on the road transport. But you should think about other modes of transport, like the kind of airplane and also the marine. And then these are the actually two. I mean, for the road transport, actually you can do that by electric vehicle easily, especially a light duty vehicle. I mean, they can be replaced by the light duty. They can be replaced by the battery electric vehicle easily. But think about the airplane. People keep saying there's no way you can run airplane, the big airplane, by using battery. I don't know. I mean, in the future, we might have very, okay, so actually you're disconnected. Okay, you come back.
Sorry, I just got cut off a little bit.
Yeah, it's still that. Okay, so
airplane. with battery.
Yeah, yeah. What happens is kind of airplane. So that's why they're talking about SAF, sustainable aviation fuel. That's a big thing, because they're thinking this only this synthetic fuel or biofuel and can do the job in the airplane, and also the marine fuel. There's no way you can just have a big chunk of battery in your ship. And then also depending on this, the high, does this synthetic fuel? I mean, biofuel can come from the biomass, or just the bio-based resources, and then but for this synthetic fuel based on the hydrogen, and because you need to have the hydrocarbon fuel, and then that hydrogen coming from the hydrogen. So that's why the big chunk of the hydrogen actually going into the transport. It's not really about fuel cell electric vehicle only. It's really about all these different modes cannot be easily replaced by this electrified powertrain. And so that's what happens there. That's and you see that there are a big chunk of the pink going to ship. So this is not really hydrogen. The hydrogen can be converted into synthetic fuel, and then it will be fed into these different modes.
I see.
Yep.
Got it.
Yep. Mm-hmm.
All right. I guess that's it for today's webinar. I would like to thank Professor Song from Seoul National University again for spending your time with us despite your late night in the US. Yeah. Thank you so much. And if you have any question for Professor Song, please feel free to reach out to him and send some email. Yeah. All right.
Thank you very much for the invitation, and it's very nice to talk to you and then do the seminar here. Thank you very much.
Bye.
Yep.